I want to tell you something that happened to me once. I was driving home late at night. No other cars on the road. The kind of night where the sky feels closer than usual, dark and heavy and full. And I pulled over. I don't know why exactly. I just did. I got out of the car and stood on the side of the road in the dark. And I looked up and I thought about something I had read that week, something that had been sitting in the back of my mind like a stone in a shoe. The thought was this: most of the universe is invisible, not just distant, not just faint, not just hard to see, invisible, completely, fundamentally, physically invisible. There is something out there, something that makes up most of the matter in the universe that does not emit light, does not reflect light, does not absorb light. It passes through everything as if everything were not there. It passes through stars, through planets, through walls, through you. Right now, thousands of particles, if there are particles passing through your body every second, without touching anything, without leaving any trace, without you feeling a thing, and we have no idea what it is. We have been looking for it for nearly a century. We have built instruments so sensitive they can detect a single atom recoiling from a collision. We have buried those instruments deep underground to shield them from everything else. We have pointed space telescopes at galaxy clusters. We have smashed protons together at nearly the speed of light, and we have not found it. Not directly, not once, and yet we are certain it exists. Not probably, not maybe, certain, because the universe tells us it is there, in the motion of stars that makes no sense without it, in the bending of light that goes further than it should, in the growth of structure across the cosmos that would be impossible without it. Dark matter, the most abundant form of matter in the universe. And we don't know what it is. I stood on the side of that road for a long time, looking up at a sky full of light, knowing that most of what was really there was invisible. And that felt, I don't know how else to say it, like the most important thing I'd ever thought about. So tonight, I want to take you there, into the dark, into the invisible, into the question that has haunted physics for nearly 100 years and has not been answered. Not yet. Get comfortable, breathe slowly, and let's begin. The problem with galaxies. When the numbers stop making sense, everything in science starts with a problem. Not a theory, a problem, something that doesn't add up, something that refuses to fit. The story of dark matter starts with a woman named Vera Rubin and a problem that refused to fit for decades. Let me set the scene. It is the 1960s and 1970s. Astronomy is in a golden age. Radio telescopes, space observatories, new instruments that can measure things that were previously impossible to measure. And Vera Rubin, an astronomer at the Carnegie Institution, is doing something that sounds straightforward. She's measuring how fast stars in spiral galaxies orbit around the center of their galaxy. This should be simple, well understood. We know how gravity works. We know that if you have a central mass and objects orbiting it, the objects further out should move slower. This is just Newton. Mercury is faster than Earth. Earth is faster than Jupiter. Jupiter is faster than Saturn. The further you are from the gravitational center, the slower you move. This is not controversial. It is the most basic possible implication of the law of gravity. So Vera Rubin expected to measure exactly this. Stars close to the center of a galaxy, fast. Stars further out, slower. Stars at the outer edge, slowest of all. What she measured instead changed everything. The stars at the outer edges of spiral galaxies were not moving slowly. They were moving fast. almost as fast as the stars near the center, far faster than the gravity from all the visible matter in the galaxy could explain. If you calculated the total mass of everything visible in the galaxy, all the stars, all the gas, all the dust, everything you could see, and then calculated how fast the outer stars should be moving based on that mass. They should be flying off into space. The visible matter was not enough to hold them in orbit at the speeds they were moving. The galaxy should be tearing itself apart. And it wasn't. The stars were there, moving fast, orbiting stably, as if there were far more mass than anyone could see. Vera Rubin measured galaxy after galaxy, spiral galaxy after spiral galaxy, the same result every time. The rotation curves, the graphs of how orbital speed changes with distance from the center were flat. Where they should have fallen off, they stayed flat. Constant speed, all the way to the edge of the visible galaxy and beyond. Something was holding those stars in orbit, something with mass, something that was not emitting light, something invisible. I want to pause here and say something about Vera Rubin, because her story is not just about dark matter. It is about what it means to do science when the answer is not what anyone expects. Rubin faced significant skepticism, not just about her data, about her right to be in the room at all. She was one of the first women to be allowed to use the Palomar Observatory. She was told at various points in her career that the kinds of questions she was asking were not important. She kept asking them anyway. She kept measuring carefully, methodically, galaxy after galaxy. She was not trying to prove anything dramatic. She was trying to understand something that didn't add up. And what she found, what the data forced her to conclude, was among the most significant discoveries in the history of astronomy. That most of the matter in galaxies is invisible. That the visible universe, the stars and gas and dust we can see, is just the luminous tip of a vast, dark iceberg. She died in 2016. She never received the Nobel Prize. Some things in science take a long time to be recognized, but the recognition came eventually. And what she found is real. The data is unambiguous. The universe contains something we cannot see. The numbers. Before we go further, let me give you the scale of the problem. When astronomers add up all the visible matter in the universe, all the stars, all the gas clouds, all the dust, all the planets, everything that emits or reflects or absorbs light in any way we can detect, it amounts to approximately 5% of the total mass energy of the universe. 5%. Dark matter is approximately 27%. And the remaining 68% is something else, something even stranger called dark energy, which we will come to. But dark matter alone, this invisible, unknown substance, is more than 5 times as abundant as everything we can see. 5 times. If you took all the stars in all the galaxies of the observable universe, all the light, all the fire, all the blazing suns, it would still be less than a quarter of the dark matter. We live in a universe that is mostly invisible, not mostly empty, mostly filled with something we cannot see, cannot touch, cannot identify. And we built everything we know, every theory, every model, every picture of the cosmos from the 5% we can actually measure. Fritz Zwicky, in the Coma cluster, the first hint of dark matter came even earlier than Vera Rubin. In 1933, a Swiss astronomer named Fritz Zwicky was studying the Coma cluster, a large cluster of galaxies, hundreds of galaxies gravitationally bound together, roughly 320 million light years away. Zwicky measured the velocities of individual galaxies within the cluster, how fast they were moving relative to each other, and he noticed something wrong. The galaxies were moving far too fast. Based on the mass he could calculate from the visible light of the galaxies, they should not have been moving that fast. The clusters should not have been gravitationally bound at all. At those velocities, the galaxies should have flown apart long ago. The cluster should not exist. But it did. Zwicky concluded that there must be additional mass, invisible mass, holding the cluster together. He called it Dunkel materia, dark matter. The term was born, the problem was born, and for 40 years, almost nobody took it seriously. It took Vera Rubin's meticulous measurements, galaxy after galaxy, the same pattern, undeniable, to force the astronomical community to confront what the data was saying. The universe contains something invisible, and we need to find out what it is. What we know it is not ruling out the obvious. The first instinct when confronted with invisible mass is to look for ordinary things that don't produce light. Dark gas clouds, cold, dead stars, black holes, planets and rocks and debris drifting in the dark between stars. There is a lot of ordinary matter we can't directly see. Why couldn't dark matter just be that? The answer is we looked. We looked carefully, and it isn't. Machos. In the 1980s and 1990s, astronomers proposed a class of objects as dark matter candidates. They called them MACOs, massive astrophysical compact halo objects, a deliberately awkward name that includes a range of possibilities. Brown dwarfs, objects not quite massive enough to ignite nuclear fusion, cold and dim. Neutron stars, collapsed stellar remnants, dense and dark. Stellar black holes, collapsed, massive stars, invisible by definition, even free-floating planets, worlds drifting without a sun. All of these exist. All of them are dark, or nearly so. Could they account for the dark matter? The test used a technique called gravitational microlensing. When a massive object passes between Earth and a distant star, its gravity bends the light from the star, briefly brightening it in a characteristic way. If the dark matter halo of the Milky Way were full of MACOs, these brightenings should happen regularly. Astronomers watched millions of stars for years, waiting for the telltale lensing events. They found some, not nearly enough. The total mass in MACOs was far too small to account for dark matter. Brown dwarfs, rogue planets, cold remnant stars, they exist, but they are not the answer. The dark matter is not ordinary matter hiding in the dark. It is something fundamentally different. Ordinary matter and Big Bang nucleosynthesis. There's an even deeper reason why dark matter cannot be ordinary matter. Any ordinary matter, protons, neutrons, electrons, the particles that make up everything we can touch, is called baryonic matter. In the first few minutes after the Big Bang, the universe was hot enough for nuclear fusion. Protons and neutrons fused into light elements, hydrogen, helium, a little lithium. The ratios in which these elements formed depend precisely on the density of baryonic matter at that time. We can measure those ratios. We can look at the oldest gas clouds in the universe, gas that has never been processed through a star, and measure how much helium, how much deuterium, how much lithium it contains. Those measurements tell us how much baryonic matter there is in the universe. And the answer matches the 5% we find from other methods. No more. The Big Bang nucleosynthesis calculations leave no room for extra baryonic matter. Whatever dark matter is, it is not made of protons and neutrons. It is not ordinary matter. It is something else. something that was not involved in the nuclear fusion of the early universe, something outside the standard chemistry of the cosmos. Neutrinos. For a while, neutrinos seemed like a promising candidate. Neutrinos are real particles, we know they exist. They're produced in nuclear reactions, in supernova, in the core of the sun. They barely interact with anything they pass through the Earth as if it were not there. They have a tiny mass. And the universe is full of them, roughly 330 neutrinos per cubic centimeter everywhere in the universe, a relic population from the Big Bang. Could neutrinos be dark matter? They have the right properties in some ways, but the calculations don't work. Neutrinos move very fast, close to the speed of light. Fast-moving dark matter, hot dark matter, would not clump together in the way needed to form galaxies. It would smooth out, diffuse, prevent the formation of the structures we observe. The cosmic web, the filaments and clusters and voids that make up the large-scale structure of the universe requires dark matter that moves slowly. Cold, dark matter. Neutrinos are the wrong temperature. They cannot explain what we see. Modified gravity. Before we go further, I should mention another possibility. Perhaps dark matter doesn't exist. Perhaps our theory of gravity is wrong. Perhaps there's a modified theory of gravity, one that behaves differently at very low accelerations at the scales typical of the outer regions of galaxies that can explain the observations without invoking any new particles. This idea called MOND, Modified Newtonian Dynamics, was proposed by physicist Mordechai Milgrom in 1983. MOND does remarkably well at explaining galaxy rotation curves, better in some ways than dark matter models. It predicts the rotation curve of a galaxy from its visible matter alone with no free parameters and gets it right. That is genuinely impressive. But MOND has problems at larger scales. It struggles with galaxy clusters where dark matter evidence is strongest. It struggles with the cosmic microwave background, the map of the early universe that requires cold dark matter to explain its structure. It does not provide a relativistic framework that naturally extends to cosmology. And there are observations like the bullet cluster, which we will come to, that seem very difficult to explain with modified gravity alone. Modified gravity remains a minority view in physics, but it is not a crazy view. It is a serious attempt to confront the data, honestly. And the fact that it exists, that physicists take it seriously enough to study it carefully, is a reminder that dark matter is genuinely an unsolved problem. Not solved by naming it, not solved by measuring its effects, only solved when we know what it actually is. The evidence that cannot be denied, what the universe is telling us. Let me take you through the evidence for dark matter, not as a list, as a story, a series of independent lines of investigation that all point to the same conclusion. Because the extraordinary thing about dark matter is not just that we have one observation that requires it, we have many from entirely different methods, using entirely different instruments, studying entirely different objects, and they all say the same thing. Something is there, something invisible, something with mass, something that shapes the universe at every scale, gravitational lensing. Einstein's theory of general relativity, published in 1915, made a prediction that seemed almost magical at the time. Gravity bends light, not because light has mass in the ordinary sense, but because gravity is not a force pulling on objects. It is a curvature of space-time, and light traveling through curved space-time follows curved paths. The more massive the object, the more curved the space-time around it. The more bent the light, The first confirmation came in 1919. Arthur Eddington observed a solar eclipse and measured the positions of stars near the edge of the sun. Their apparent positions were shifted slightly compared to their positions when the sun was elsewhere in the sky. The light from those stars had been bent by the sun's gravity. Einstein was right. Now, if a galaxy or cluster of galaxies sits between us and a more distant object, its gravity will bend the light from that distant object. It would act as a lens, a gravitational lens. The distant object will appear distorted, stretched into arcs, sometimes into multiple images, sometimes into a complete ring surrounding the lensing object. This is called strong gravitational lensing, and it is extraordinary to look at. Images from the Hubble Space Telescope show galaxy clusters surrounded by arcs, smeared, curved images of galaxies far behind the cluster, their light bent by the cluster's gravity. The geometry of the lensing depends on the mass of the lens. Precisely, quantitatively, by analyzing the distortions, by measuring how much the background galaxies have been bent, and by how much astronomers can calculate the total mass of the lensing cluster, not just the visible mass, the total mass, including any dark matter. And the mass required to produce the observed lensing is always far more than the visible mass, by the same factor as in rotation curves, 5 times more. The gravitational lensing evidence for dark matter is independent of rotation curves. Different method, different objects, same answer. The cosmic microwave background. In 1965, 2 radio astronomers, Arno Penzias and Robert Wilson, detected a faint microwave signal coming uniformly from all directions in the sky. They couldn't get rid of it. They cleaned their antenna. They removed pigeons that had nested in it. The signal remained. It was the cosmic microwave background, the afterglow of the Big Bang. The universe, when it was about 380,000 years old, transitioned from an opaque plasma to a transparent gas. The photons, the light that had been trapped in the plasma, were suddenly free to travel. They have been traveling ever since, for 13.8 billion years, cooling as the universe expanded, redshifting from visible light to microwave radiation, and filling the entire sky with a faint, nearly uniform glow. Nearly uniform, not perfectly uniform. When we map the cosmic microwave background with precision, which we have done with the COBE, WMAP, and Planck satellites, we see tiny temperature fluctuations, 1 part in 100,000, tiny variations in the temperature of the early universe. These fluctuations are the seeds of everything. The places where the matter was slightly denser, the places where gravity would eventually win, where galaxies and clusters and the cosmic web would eventually form. The pattern of these fluctuations, their size, their distribution, their precise statistical properties, depends on what the universe was made of. On the proportions of ordinary matter, dark matter, and dark energy. When physicists fit theoretical models to the CMB data, they find one model that matches the observations almost perfectly. A model with approximately 5% ordinary matter, 27% dark matter, 68% dark energy. The CMB is not measuring galaxy rotation curves. It is measuring the acoustic oscillations of the early universe, the sound waves in the plasma of the infant cosmos. And those sound waves encode the composition of the universe, and they tell us dark matter is real. The bullet cluster, if there is one piece of evidence for dark matter that I find most compelling, most visceral, most direct, it is the bullet cluster. The bullet cluster is the result of a collision between 2 galaxy clusters. About 150 million years ago, two clusters, each containing hundreds of galaxies and vast amounts of hot gas, collided, passed through each other. The galaxies themselves, moving so fast and spaced so far apart, passed through each other almost without interaction, like two swarms of bees flying through each other. The hot gas, the ordinary matter, did interact. It collided, it shocked, it heated up, it slowed down. The hot gas visible in X-rays is now concentrated in the region between the two clusters where the collision happened. But the dark matter, if dark matter exists, and if it barely interacts with anything, should have passed through the collision without slowing down. It should be moving with the galaxies, ahead of the gas. And when astronomers mapped the gravitational lensing of the bullet cluster, measuring where the mass is by how much background galaxies are distorted, that is exactly what they found. The mass is not where the gas is. The mass is where the galaxies are, ahead of the gas, in two separate clumps. The dark matter passed through the collision. The ordinary matter got stuck. The bullet cluster is the most direct observational evidence for dark matter as a physical substance, not a modification of gravity, not a property of ordinary matter we hadn't accounted for, an actual substance separate from ordinary matter that passed through a cluster collision while the gas piled up behind. When I first looked at the image, the X-ray image overlaid with the lensing map, the gas in one place and the mass in another, something clicked. Something felt real. The dark matter was there, not everywhere, not diffuse, in a specific place, separated from the gas by a specific collision, visible in its effect on the light of distant galaxies behind it. The invisible thing had left a shadow, and we could see the shadow. Strukturformation. One of the most powerful lines of evidence for dark matter comes from the large-scale structure of the universe, the cosmic web, the filaments and voids and clusters. The way galaxies are not randomly distributed, but instead trace a vast three-dimensional network. For this structure to exist, for the tiny fluctuations in the early universe to have grown into the cosmic web we observe today, there needs to be something to do the work. Ordinary matter alone cannot do it. In the early universe, before the CMB was released, ordinary matter was coupled to the photons trapped in the hot plasma, unable to collapse under gravity because the radiation pressure resisted it. It could not start forming structure early. Dark matter was not coupled to the photons. It could start collapsing immediately. It formed the first gravitational halos, dense regions that attracted ordinary matter once the plasma released it. The dark matter provided the scaffolding. The ordinary matter fell into the scaffolding. The galaxies formed at the intersections. The cosmic web is fundamentally a map of the dark matter distribution. The galaxies are where they are because of where the dark matter was first. Without dark matter or something performing its exact role, the universe would look completely different. No cosmic web, no galaxy clusters, perhaps no galaxies at all, or galaxies so different from what we see that they would be unrecognizable. The universe, we live in the particular universe with its particular arrangement of structure, requires dark matter, or something that behaves exactly like it. What it might be, the leading candidates, if dark matter is not ordinary matter, not protons, not neutrons, not electrons, not neutrinos, not black holes made of ordinary collapsed stars, then what is it? This is the great open question. And there are candidates, theoretical particles that have been proposed, particles that would behave the way dark matter behaves. Let me take you through the main ones. Not as a textbook, as a tour of possibilities. each one a doorway into a different way of thinking about what the universe might be made of. WIMPs, the leading candidate. For decades, the leading candidate for dark matter was the WIMP, weakly interacting massive particle. A particle that has mass, enough mass to affect gravity, but interacts with ordinary matter only through the weak nuclear force. And gravity, not electromagnetism, not the strong nuclear force, just gravity and the weak force. The weak force is the force responsible for radioactive decay, for the nuclear reactions that power the sun, for the processes that turn neutrons into protons. Particles that interact only through the weak force are extraordinarily difficult to detect. They can pass through almost anything, but not quite anything. Occasionally, rarely, a WIMP should collide with an atomic nucleus. Not often enough to be easily detected, but with a sensitive enough instrument buried deep enough underground to shield it from everything else. It should be possible. The appeal of WIMPs goes beyond just explaining dark matter. It comes from a beautiful coincidence. If you calculate how many WIMPs would have been produced in the Big Bang, if WIMPs exist with the right mass and the right interaction strength to be weakly interacting, and if you then calculate how many would have survived annihilation as the universe cooled, you get approximately the right density, the density that matches the observed dark matter density. This is called the WIMP miracle. The idea that a particle motivated by completely independent reasons, by the mathematics of the standard model of particle physics, by theories of supersymmetry, would naturally produce the right amount of dark matter. Without any fine-tuning, without any special adjustment. It just works out. When two independent lines of reasoning, cosmology and particle physics, point to the same answer, physicists pay attention. The WIMP miracle made WIMPs the most compelling dark matter candidate for 30 years. The search for WIMPs has been one of the largest experimental efforts in modern physics. Underground detectors, buried in mine shafts, in tunnels under mountains, in deep caves. The Large Underground Xenon Experiment, the Pandax experiment in China, the Xenon experiments at Gran Sasso in Italy, the cryogenic dark matter search, tanks of liquid xenon or germanium crystals cooled to near absolute zero, surrounded by layers of shielding, deep underground, waiting for the 1 in a billion collision between a WIMP and an atomic nucleus that would register as a tiny recoil, a tiny pulse of light or heat, the signature of dark matter. They have not found it. Years, decades, increasingly sensitive instruments. The detection threshold drops lower and lower, finer and finer, smaller and smaller recoils that can be measured, and still, nothing, no signal, no dark matter. The absence of a signal is itself information. It rules out WIMPs of certain masses and interaction strengths, the allowed parameter space, the range of masses and interaction strengths a WIMP could have and still not have been detected gets smaller every year. Not eliminated, but constrained. WIMPs are still possible, but the WIMP miracle is looking less miraculous. The simplest WIMPs, the ones predicted by the simplest theories, should have been found by now. They haven't been. Something is either wrong with the theories, or our detectors are not quite sensitive enough yet, or WIMPs are not dark matter. Axiom. If WIMPs are the extrovert of dark matter candidates, flashy, well-motivated, extensively searched for, then actions are the introvert, quiet, theoretical, motivated by a completely different problem in physics. The axiom was proposed in 1977 by physicists Roberto Peccei and Helen Quinn. not to solve the dark matter problem, but to solve a different problem, the strong CP problem. The strong nuclear force has a peculiar feature. The mathematics allow for a parameter called theta that would make the strong force violate a fundamental symmetry called CP symmetry. If theta were large, neutrons would have an electric dipole moment. They would be slightly asymmetric in their charge distribution. Measurements show neutrons are almost perfectly symmetric. Theta must be extraordinarily small, almost exactly zero. But why? There is no obvious reason in the theory why theta should be small. This fine-tuning, this apparently accidental cancellation, is the strong CP problem. Peche and Quinn proposed a new symmetry now called the Peche-Quinn symmetry that would dynamically drive theta to zero. When this symmetry is slightly broken, a new particle is predicted. The axion. The axion would be extraordinarily light, far lighter than an electron, perhaps by many orders of magnitude. It would barely interact with anything, but it would be produced in enormous quantities in the early universe. And despite its tiny individual mass, there would be so many of them that the total mass could account for the dark matter, a dark matter candidate born from a completely different problem. Solving two puzzles with one particle. The axion has properties that make it detectable in principle. In the presence of a strong magnetic field, actions can convert into photons, tiny photons. In the microwave or radio range, this conversion is the basis for axion detectors. The most famous axion detector is the ADMX, the Axion Dark Matter experiment. A large superconducting magnet, a microwave cavity tuned to the frequency at which actions of a particular mass would convert, cooled to near absolute zero. Listening for a faint radio signal, the signal of an axion converting into a photon in the magnetic field, in the cavity. The experiment has been running for years. It has not found the axion, but it has not ruled it out. The possible mass range for actions is vast, many orders of magnitude. The experiment covers a tiny slice of that range at a time. The search continues. Sterile neutrinos. Regular neutrinos, the ghost particles produced in nuclear reactions, interact via the weak force. Barely, but they do. A sterile neutrino would be a neutrino that doesn't even interact via the weak force, interacting only via gravity, truly inert, invisible in every way except gravitational. Sterile neutrinos are predicted by some extensions of the standard model of particle physics. They could have been produced in the early universe. They would be stable, not decaying into anything we could easily detect. And they could account for the dark matter. One potentially observable signature, sterile neutrinos might very occasionally, with an extremely small probability, decay into a regular neutrino and a photon. An X-ray photon offers specific energy depending on the sterile neutrino mass. In 2014, astronomers announced something remarkable, a signal, a faint line in X-ray observations of galaxy clusters at an energy of 3.5 kiloelectron volts, exactly in the range where a sterile neutrino of a certain mass would decay. The same signal was found in multiple galaxy clusters. In the center of the Milky Way, in the Andromeda galaxy, places where dark matter is expected to be dense. For a while, the physics community was electric with excitement. Was this it? Was this dark matter? The excitement was tempered. Other telescopes looked for the signal. Some found it, some didn't. Some found it in some observations, but not others. The signal remains controversial. neither confirmed nor definitively ruled out. It might be dark matter. It might be a background emission from potassium ions in the hot gas of galaxy clusters, mundane atomic physics, mimicking something exotic. The 3.5 keV line remains an open question, one of the most watched puzzles in astrophysics. If future X-ray telescopes, the next generation, with higher resolution and sensitivity, confirm the signal consistently across many objects, it might be one of the most important discoveries in the history of science. If it disappears with better data, it would be a reminder that science requires patience, that hints are not discoveries, that the universe does not give up its secrets easily. Primordial black holes. In 2015, something happened that shook physics. Gravitational wave detectors LIGO in the United States detected the merger of two black holes. That was already extraordinary. The first direct detection of gravitational waves. Einstein had been right again. But the black holes had unusual masses, larger than the masses typical of black holes formed from dying stars. The detection reignited interest in an old idea, primordial black holes. Black holes not formed from the collapse of stars, but formed in the early universe in the first fractions of a second after the Big Bang, when density fluctuations could have been extreme enough to collapse directly into black holes. Primordial black holes would be dark. They would not emit light. They would have mass. They would be distributed throughout the universe in the way dark matter is distributed. Could primordial black holes be dark matter? The idea has been tested extensively. Gravitational microlensing surveys. The lack of distortions in the cosmic microwave background. The accretion effects that would heat the intergalactic medium if many black holes were drifting through it. The conclusion: primordial black holes of a simple single mass cannot account for all the dark matter. Some mass ranges are definitively ruled out, but there remain windows. Ranges of masses where primordial black holes are still allowed, including a range around asteroid mass, black holes, the mass of a mountain, the size of a proton. In this mass range, the constraints are difficult to measure. The detection methods are hard. The possibility remains. Not the leading candidate, but not eliminated. Ultralight dark matter, fuzzy dark matter. Here is an idea so strange that when I first encountered it, I thought it was science fiction. What if dark matter is a single quantum field, not particles in the traditional sense, but a wave-like quantum substance with a mass so incredibly small that a single quantum of it has a wavelength thousands of light years across? This is called ultralight dark matter, or fuzzy dark matter. The particle would have a mass perhaps 22 orders of magnitude lighter than the electron. So light that the quantum uncertainty in its position, the quantum fuzziness that gives the idea its name, smears it out over kiloparsec scales. Individual particles of dark matter, millions of light years across. Quantum objects the size of galaxies. It sounds impossible, but the mathematics work. And fuzzy dark matter makes specific predictions that differ from ordinary cold dark matter. In particular, it predicts the suppression of structure at small scales, fewer small galaxies, smoother central regions of galaxies that seem to match some observations better than the standard cold dark matter model. The small-scale structure of the universe is one of the places where the standard model has difficulties. It predicts far more small satellite galaxies around the Milky Way than we observe. Fuzzy dark matter might explain why. I find ultralight dark matter genuinely beautiful. not just because the physics is interesting, but because it represents a kind of thinking that refuses to be limited by familiar categories. Particle, wave, object, field. These distinctions at the quantum level are not as sharp as they seem in the everyday world. And the universe does not organize itself around our categories. If dark matter is a quantum field with a mass so small that its quantum wavelength is galactic in scale, then the galaxies themselves are, in a sense, sitting inside a quantum object. The dark matter halo of the Milky Way is not a cloud of particles. It is a quantum condensate, a single macroscopic quantum state. The galaxies inside a quantum object the size of the galaxy. The mind refuses to contain this, but the mathematics allows it, and the universe does not care what the mind can contain. The search is how we are looking. The search for dark matter is one of the great experimental enterprises of modern science. It spans three approaches: direct detection, trying to catch dark matter particles colliding with ordinary matter in underground detectors; indirect detection, looking for signals produced when dark matter particles annihilate each other in space: gamma rays, neutrinos, antimatter, collider production, trying to create dark matter particles in particle accelerators like the Large Hadron Collider by smashing ordinary particles together with enough energy to produce new particles. Each approach has its strengths, each has its limitations, and so far all three have come up empty. Not conclusively, not finally. Butsail, underground detectors. The underground detectors are extraordinary machines. Take the Lux Zeppelin experiment, located in the Sanford Underground Research Facility in South Dakota. Nearly a mile underground, deep enough that the rock above filters out almost all cosmic rays. The detector itself, 10 tons of liquid xenon, cooled to about minus 100 degrees Celsius, surrounded by a 70,000-liter tank of water for additional shielding, instrumented with hundreds of photomultiplier tubes that can detect individual photons. The idea: if a dark matter particle collides with a xenon nucleus, the nucleus recoils. That recoil produces a tiny flash of light and a small ionization signal. The combination of the two signals, their ratio, their timing, identifies the event as a nuclear recoil. The detector records every recoil above a certain threshold. Then physicists look for an excess, more events than expected from known backgrounds. The dark matter signal. The backgrounds are the difficulty. Everything produces backgrounds. Radioactive impurities in the detector materials. Cosmic rays that penetrate even a mile of rock. Neutrinos, ghost particles from the sun, from supernovae, from the atmosphere that occasionally scatter off nuclei, just like dark matter would. The detector cannot distinguish a neutrino scatter from a dark matter scatter. This is called the neutrino floor, the background noise level set by neutrinos that cannot be shielded against. As detectors get more sensitive, they approach the neutrino floor. Beyond it, new techniques will be needed, new ways to distinguish the neutrino signal from a potential dark matter signal. The sensitivity of these detectors has improved by many orders of magnitude over the past 30 years, and they have not found dark matter. The non-detection has ruled out large portions of the WIMP parameter space, but not all. The search continues. Indirect detection. If dark matter is made of particles, and if those particles are their own antiparticles, as WIMPs are predicted to be, then two dark matter particles that meet should annihilate. converting their mass into energy into gamma rays, into neutrinos, into electron-positron pairs, into a shower of ordinary particles. The densest concentrations of dark matter, the centers of galaxies, globular clusters, dwarf galaxies that are almost pure dark matter, are places where dark matter particles should be meeting each other, annihilating, producing a flux of gamma rays above the ordinary astrophysical background. The Fermi Gamma Ray Space Telescope orbiting Earth since 2008 has been mapping the gamma ray sky with extraordinary sensitivity. It has found many gamma ray sources. It has found what appeared to be an excess of gamma rays from the center of the Milky Way, an excess over and above what can be explained by known sources. For a while, it seemed like a signal. The spectrum was consistent with dark matter annihilation. The spatial distribution was consistent with dark matter density profiles. Physicists were cautious but excited, but the center of the Milky Way is a complicated place. There are many potential sources of gamma rays there. Pulsars, rapidly rotating neutron stars, produce gamma rays. There may be many unresolved pulsars in the galactic center, enough to produce exactly the excess that was observed. The current state, the galactic center gamma ray excess, remains unexplained. It is consistent with dark matter annihilation. It is also consistent with a population of unresolved pulsars. With better data, with more observations, with more detailed modeling of the astrophysical backgrounds, the answer may become clearer, or it may remain ambiguous. The universe is good at ambiguity. The Large Hadron Collider. In Geneva, Switzerland, under the French-Swiss border, there is a tunnel, circular, 27 kilometers in circumference. Inside the tunnel, a particle accelerator, the Large Hadron Collider. Protons accelerated to 99.9999991% of the speed of light collided at 4 intersection points. The energy of the collision, equivalent to the energy conditions of the universe when it was a fraction of a nanosecond old, is high enough to produce particles that do not normally exist in our low-energy universe. In 2012, the Higgs boson was discovered there, predicted by theory 47 years before its discovery, the final missing piece of the standard model of particle physics. Its discovery was one of the greatest triumphs in the history of science. Could the LHC produce dark matter? In principle, yes. If dark matter particles exist and interact with ordinary matter even weakly, the collisions at the LHC might occasionally produce them. The dark matter particles themselves would escape the detector undetected, but their production would be inferred from what is missing. If particles collide and some energy and momentum simply disappear, carried away by invisible, undetected particles, that is the signature of dark matter production, missing energy, the signature of the invisible. The LHC experiments, ATLAS and CMS, enormous detectors the size of cathedrals, have looked for exactly this signature extensively in billions of collisions and found nothing unexpected. No missing energy beyond known sources. No dark matter, at least not at the energies the LHC can reach. This rules out some dark matter models. Not all. Dark matter might exist but require higher energies to produce. Or it might interact with ordinary matter through a force so weak that even the LHC cannot produce it in detectable quantities. The silence, 3 decades of searching, underground detectors, space telescopes, particle accelerators, the most sensitive instruments ever built by human civilization, the most sophisticated experiments ever conceived, and the most common form of matter in the universe has remained stubbornly, completely invisible. I want to sit with that for a moment because it is easy to present the null results as failures, as the scientific community is somehow letting us down. But that is not how science works. The absence of a signal is information. Every non-detection rules out possibilities. Every ruled out possibility constrains what dark matter can be. The parameter space of allowed dark matter candidates, the range of masses and interaction strengths that remain possible, is narrower now than it was 30 years ago. We know more about what dark matter is not. That is real progress. And the search is ongoing. New detectors, new technique, new theoretical ideas. The universe has kept this secret for nearly a century. It may not keep it forever. The dark matter halo, the invisible structure around us. Right now, as you lie here, as you breathe, as the room around you settles into quiet, you are inside dark matter. The Milky Way is surrounded by an enormous halo of dark matter, not a thin shell. A vast, three-dimensional distribution of dark matter extending far beyond the visible disk of the galaxy, perhaps 200,000 to 300,000 light years in radius, many times larger than the luminous disk. And you are inside it. We all are. The dark matter halo is not distributed uniformly. It is denser toward the center, toward the galactic center, 26,000 light years away. It thins out toward the edges. At our position in the Orion Arm, 26,000 light years from the center, the density of dark matter is estimated at about 0.3 proton masses per cubic centimeter. That sounds small. It is small. But it means that in the room you're in right now, a roughly 50 cubic meter space, there are approximately 300 billion dark matter particles. If the most common estimate for dark matter particle mass is correct, 300 billion dark matter particles in your room right now, moving through you, through the walls, through the floor, through the planet beneath you, invisible, undetectable by any instrument we have. But there, the universe, having saturated even the space you occupy with its most abundant form of matter, the structure of the halo, the dark matter halo, is not smooth. Computer simulations, enormous calculations, tracking the gravitational evolution of dark matter from the early universe to the present predict that the halo has structure subalos, dense regions within the larger halo, perhaps thousands of small dark matter clumps orbiting within the Milky Way's dark matter distribution. Some of these subhalos are massive enough to have captured ordinary matter, to have formed small satellite galaxies. The dwarf galaxies orbiting the Milky Way sculptor, Fornax, Draco, Ursa Minor, and dozens of others are thought to be ordinary matter sitting in dark matter subhalos. The dwarf galaxies are, in fact, among the best places to look for dark matter. They are the most dark matter-dominated objects known. In some of them, dark matter outweighs ordinary matter by factors of thousands to one. They are nearly pure dark matter, with a thin dusting of stars to make them visible. The simulations predict far more subhalos than we observe satellite galaxies. This is one of the long-standing problems of the cold dark matter model, the missing satellites problem. The theory predicts thousands of dark matter subhalos around the Milky Way. We observe only about 50 satellite galaxies. Where are the rest? Several explanations have been proposed. Most subhalos may simply not have formed stars. They captured gas in the early universe, but the gas was evaporated by the ultraviolet radiation of the first stars. Dark matter halos without ordinary matter inside them, invisible even to our best telescopes. or the dark matter model itself may need modification. The small-scale predictions of cold dark matter may be wrong at some level. The missing satellites problem is one of the active frontiers of dark matter research. And it illustrates something important. Even in the regime where dark matter's existence is not in doubt, the details, the precise distribution, the small-scale structure are still being worked out. Dark matter is real. What dark matter is exactly, and how it behaves in detail, that is still being learned. The early universe, dark matter's role in building everything. Let me take you back to the beginning, not of the Earth, not of the solar system, to the beginning of the universe itself, to the first fractions of a second, when everything was so hot and dense that ordinary matter as we know it did not yet exist, just a plasma of quarks and gluons and leptons and photons, an undifferentiated, blazing sea of energy and dark matter already there, already separate from ordinary matter, already beginning to move. In the first second, dark matter begins to cool. Its particles, whatever they are, slow down, still too hot to clump, but cooling as the universe expands, as the temperature drops. At some point, when the universe is seconds to minutes old, the interaction rate for dark matter drops below the expansion rate. Dark matter freezes out. Its number density stops changing. Whatever quantity existed at that moment, whatever density was set by the balance of production and annihilation, that is what we have today. The relic density, this is the calculation behind the WIMP miracle. If WIMPs froze out with the right interaction strength, the relic density matches the observed dark matter density. The same physics that set the number of dark matter particles in the universe also set the conditions for Big Bang nucleosynthesis. The same physics that produced the cosmic microwave background. Everything in the early universe is interconnected. The first structures. In the first few 100,000 years, the ordinary matter is locked in a plasma, coupled to the photons, unable to collapse under gravity. The sound waves we discussed earlier, the pressure waves, the acoustic oscillations are the imprint of this coupling, but dark matter is free. From the moment it freezes out, dark matter begins to respond to gravity. It begins to clump, slowly, imperceptibly, but the slightly denser regions become denser still. The slightly underdense regions become emptier. Over hundreds of thousands of years, dark matter halos form. The first gravitational structures in the universe, the seeds of everything. When the ordinary matter finally decouples from the photons, when the plasma becomes a neutral gas, when the CMB is released, it falls into the potential wells already carved by the dark matter. It falls into the halos. It pools in them. It cools. It forms molecular hydrogen. The first molecular hydrogen clouds, the raw material for the first stars that change everything. Without dark matter, to create the gravitational scaffolding, the ordinary matter would not have had anything to fall into. The slight density fluctuations in the early universe would not have been amplified fast enough. Structure formation would have been delayed. Perhaps not enough time would have passed for galaxies to form in the current age of the universe. Perhaps no galaxies at all. Perhaps a universe of diffuse gas, no stars, no planets, no chemistry, no biology, no Milky Way for our solar system to sit inside, no solar system, no Earth, knows. Dark matter is not just an astronomical curiosity. It is the reason the universe is habitable, the reason there is structure, the reason there are stars and planets and the conditions for anything at all to exist. The invisible substance made everything visible possible. Dark matter and dark energy, two darknesses, two mysteries. Dark matter and dark energy are often mentioned together. Both are dark, both are invisible, both are unknown, but they are completely different things. And I want to make that distinction clear, because conflating them, which is easy to do, obscures what is actually mysterious about each. Dark matter is matter. It has mass. It responds to gravity. It clumps. It forms structure. It makes galaxies rotate faster than they should. It bends light. It is the scaffold on which the visible universe is built. Whatever it is, particles, fields, primordial objects, it is stuff, physical stuff, with gravitational effects. Dark energy is not matter. It is not stuff in the ordinary sense. It is a property of space itself. Empty space, not empty in the sense of containing nothing. Empty space, according to quantum mechanics, seethes with virtual particle-antiparticle pairs, fluctuating, popping in and out of existence. The quantum vacuum has energy. Dark energy may be the energy of the vacuum, a constant energy density distributed uniformly throughout all of space, that does not clump, that does not become more concentrated in dense regions, that is simply the same everywhere, always, a background energy that the universe is saturated with. And this energy has a strange property. It causes the expansion of the universe to accelerate, not decelerate, as gravity would. Accelerate. As the universe expands, it creates more volume. More volume means more vacuum energy. More vacuum energy means more accelerating expansion, creating more volume, more vacuum energy, more acceleration, a feedback loop. The universe is not just expanding, it is expanding faster and faster, pushed apart by the energy of the vacuum itself. This was discovered in 1998. Two teams of astronomers studying type Ia supernovae standard candles whose intrinsic brightness is known, allowing distance measurements found that distant supernovae were dimmer than expected, farther away than they should be. The universe was expanding faster in the past than the deceleration models predicted. The expansion was not slowing down, it was speeding up. The discovery was awarded the Nobel Prize in Physics in 2011. Saul Perlmutter, Brian Schmidt, Adam Rees, three people who discovered that the universe is doing something no one expected, accelerating into emptiness. The problem with dark energy is even deeper than the problem with dark matter. At least with dark matter, we have a fairly clear picture of what it does and where it is. With dark energy, even the basic physics is baffling. If dark energy is the energy of the quantum vacuum, the energy predicted by quantum field theory, the predicted value is approximately 10 to the power of 120 times larger than the observed value, 1 followed by 120 zeros. The largest discrepancy between theory and observation in the history of science. The theory predicts something 10, 120 times too large, which means either the theory is catastrophically wrong, or there's some mechanism that cancels almost all of the vacuum energy, leaving only this tiny residual, a cancellation accurate to 120 decimal places. The fine-tuning required would be extraordinary. No one knows why this happens. No one has a satisfying explanation. Dark energy remains deeply mysterious, and the universe is mostly dark energy, 68%, the largest component and the least understood. I think about this sometimes. We live in a universe that is 5% ordinary matter, 27% dark matter, 68% dark energy. We have understood the 5% well enough to build civilizations, to develop language and art and science, to look up at the sky and ask what is there. We have detected the 27% through its gravitational effects. We know it is there. We do not know what it is. We have measured the 68% through its effect on cosmic expansion. We have given it a name. We do not understand it at all. The universe is a mystery we have barely begun to read. And we have been asking the questions for about 400 years, simulating the universe. What computers tell us about the dark? We cannot see dark matter directly. We cannot hold it. We cannot run an experiment where we create a galaxy and watch dark matter form within it. But we can simulate it. The last 30 years have seen an extraordinary development. Cosmological simulations, enormous computer calculations that start with the initial conditions of the early universe, the tiny density fluctuations imprinted in the CMB, and evolve them forward in time, tracking the gravitational interactions of billions of particles, watching the universe form from gas and dark matter into stars and galaxies, into the cosmic web. The Millennium Simulation, the Illustris Project, Eagle, Illustris TNG, Simba. Each generation more detailed than the last, more particles, more physics, including not just gravity but gas dynamics, star formation, supernovae, black hole feedback. The simulations have become extraordinarily good at reproducing the large-scale structure of the universe. The cosmic web, they produce the distribution of galaxies across hundreds of millions of light years, matches what we observe with remarkable fidelity. Not perfectly, but well enough that the basic model, cold dark matter plus dark energy plus ordinary matter, is not in serious doubt at large scales. The simulations are not just tools for checking the theory. They are tools for making predictions. If dark matter behaves a certain way, if it has a particular mass, or interacts with itself in some small way, or has some quantum mechanical property, the simulations predict specific observable signatures, predictions that observers can then test. The back and forth between simulation and observation is one of the most productive dialogues in modern cosmology. One of the things I find most striking about the simulations is the emergence of structure. You start with a nearly uniform gas, just a tiny fluctuations, 1 part in 100,000, and you watch gravity work over millions of years, over billions of years. The gas flows, the dark matter halos form. The gas cools within the halos, stars begin to ignite, galaxy form. The galaxies are drawn together by gravity. They cluster. The clusters connect along filaments. The cosmic web emerges. All of this, the entire magnificent structure of the universe, from tiny fluctuations, gravity amplifying those fluctuations, dark matter providing the scaffolding, ordinary matter following, the universe building itself from almost nothing by its own laws, without anyone directing it. The problems, the simulations are good, but they are not perfect. And the places where they fail are important. They point to something still unknown, something still missing. The missing satellites problem. Simulations predict far more small satellite galaxies than we observe. The core cusp problem. Simulations predict that dark matter density should increase steeply toward the centers of galaxies, a cusp. Observations suggest many galaxies have flatter cores. The profiles don't match. The too big to fail problem. Simulations predict some massive dark matter subhalos that should certainly have formed visible galaxies. They are too big to have failed to form stars. But the satellite galaxies we observe are less massive than those predicted subhalos. These are the small-scale structure problems of cold dark matter. They may have solutions in ordinary astrophysics, the feedback from supernovae, the heating by UV radiation from the first stars, processes that smooth out the cusps and suppress dwarf galaxy formation, or they may require a modification of the dark matter model itself. Dark matter that self-interacts. Dark matter that is warm rather than cold. Fuzzy dark matter. Some hybrid. The simulations are the testing ground. Every new model of dark matter generates new predictions, new simulations, new comparisons with observations. The search continues. In silicon as much as in stone. The philosophical weight, what the dark means. I want to step back from the physics for a moment. From the rotation curves and the microlensing and the CMB, and think about what it means for our place in the universe, what it means that we are made of the minority substance, the 5%. The odd stuff. For most of human history, the question of what the universe is made of was answered with the world around us. Earth, water, fire, air, the four elements of ancient philosophy. Or later, atoms. Democritus imagined indivisible particles, atoms, as the fundamental stuff of the world. He was not wrong. 2,000 years before the evidence was clear, he had the right idea. The world is made of atoms. Proton, neutron, electron. The periodic table, chemistry, the breathtaking diversity of matter organized into a single, coherent framework. We thought we understood what things were made of. We were proud of that understanding. And then, Fritz Zwicky looked at the coma cluster. Vera Rubin measured rotation curves. The CMB told us its secrets. And it turned out that everything we know, every atom in every substance we have ever touched, every molecule we have ever studied, every star we have ever observed is 5%. The ordinary stuff, the stuff that makes atoms, is 5%. The universe made the decision, or rather, the laws of physics resulted in a universe where most of the matter is something else. Something that doesn't make atoms, doesn't make chemistry, doesn't make stars, just pulls, gravitates, provides the scaffolding, and watches if watching with something dark matter could do as the tiny fraction of ordinary matter assembles itself into complexity, into stars, into planets, into biology, into minds. There's something deeply strange about being the minority substance. We are the unusual stuff, the exotic 5%, the matter that formed chemistry and life and awareness, the matter that is, in some sense, cosmically exceptional. Dark matter doesn't make galaxies. It holds them together, but it doesn't become them. It doesn't participate in the formation of structure beyond the larger scales. It is the framework, the invisible framework, and we, ordinary matter, are what happens inside the framework. The exceptional, chemical, living, thinking stuff, living inside a universe mostly made of something else, something silent, something invisible, something that does not know we are here. The question of consciousness, I find myself, when I think about dark matter for long enough, arriving at a strange question. Is consciousness itself the rarest thing in the universe? Not dark matter, not dark energy, but awareness, the capacity to wonder. Dark matter is abundant. It is 27% of everything. It has been here since the beginning, It will be here after everything we know is gone. But it has no experience. As far as we know, it does not wonder what ordinary matter is. It does not search for the answer to its own nature. It does not build instruments to detect itself. We are the rare, exceptional, cosmically unusual stuff, made of the minority matter, organized into configurations so complex that something happened, something extraordinary. Awareness, the universe knowing itself through us, through the 5%, through the strange chemical, biological, conscious, wondering fraction that looks at the other 95% and asks, what are you? The future of the search, what comes next? The search for dark matter is not ending. Despite the null results, despite the decades of non-detection, despite the WIMP miracle looking less miraculous, the search is intensifying. New ideas, new experiments, new approaches, next generation underground detectors. The Lux Zeppelin experiment is running. Its successor is already being designed. A liquid xenon detector with hundreds of tons of target material, approaching and eventually passing the neutrino floor. At that point, the detector will begin to see neutrinos, thousands of neutrino scattering events per year. Above that background, buried within it, perhaps a dark matter signal. If it is there, if WIMPs exist, in the mass range still allowed, extracting a dark matter signal from a neutrino background will require new techniques. Using the directionality of neutrino events which come from specific directions like the sun to distinguish them from dark matter events, which should come from all directions equally, or using the modulation signal. As the Earth orbits the sun and the solar system moves through the dark matter halo of the Milky Way, the rate of dark matter interactions should vary. Higher in June, when the Earth's orbital velocity adds to the solar system's velocity through the halo. Lower in December, when it subtracts. A seasonal modulation, about 3% variation in rate. If a detector sees such a modulation correlated with the right phase of the year, it would be a powerful signature of dark matter. One experiment, DAMA, Libra, an Italian detector using sodium iodide, has claimed to see exactly this modulation for over 20 years, consistently with high statistical significance, but no other experiment has reproduced it. Different target material, different location, no modulation. The DAMA signal remains mysterious and controversial. It might be dark matter. It might be some unknown systematic effect specific to sodium iodide. New experiments using sodium iodide, cosin, and anase are running specifically to test the DAMA claim. The answer is coming. Soon, perhaps, action experiments, new axion detectors are being built. Abracadabra. Eistats. The axion dark matter experiment continues to upgrade. New designs, plasma haloscopes, dielectric haloscopes, cover different mass ranges. The theoretical motivation for actions, if anything, has grown stronger. They remain compelling, not yet discovered, but compelling gravitational wave astronomy. The detection of gravitational waves has opened a new window. If dark matter consists of primordial black holes in certain mass ranges, their mergers should produce gravitational waves, detectably by LIGO and Virgo. The statistics of black hole mergers, their masses, their spins, their rates can constrain the contribution of primordial black holes to dark matter. The analysis is ongoing. The constraints are tightening. the Vera Rubin Observatory. In Chile, a new telescope is coming online. The Vera Rubin Observatory, named fittingly for the woman who made dark matter undeniable. Its legacy survey of space and time will photograph the entire visible southern sky every few nights. For 10 years, mapping billions of galaxies, measuring the shapes of those galaxies with extraordinary precision, the subtle distortions from gravitational lensing, the dark matter distribution mapped across the entire observable universe, the most detailed map of the invisible ever attempted. The Roman Space Telescope, NASA's Nancy Grace Roman Space Telescope, named for the mother of Hubble, will survey the sky in infrared, mapping dark matter through weak lensing across enormous swaths of the sky, complementing the Rubin Observatory. Together, the two surveys will provide constraints on dark matter at every scale, from individual galaxies to the cosmic web. The next 20 years. I think about what might happen in the next 20 years, and I find myself cautiously, carefully optimistic, not because we are close, not because the next experiment will definitely find it, but because the tools are improving, the ideas are diversifying, the search is widening. 30 years ago, almost all the experimental effort was directed at WIMPs in a specific mass range. Now the search spans many orders of magnitude in mass, many types of particles, many detection strategies. The parameter space is being explored systematically, and somewhere in that parameter space, if dark matter is particles, there's an answer. A mass, an interaction strength, a signature that will be found when the right instrument looks in the right place, in the right way, or the answer will come differently, not from a particle detector, from a telescope, from a pattern in the gravitational lensing maps, from the statistics of galaxy mergers, from a signal in the X-ray sky, from a gravitational wave background. Science does not always find the answer where it is looking. Sometimes the answer appears in data collected for a completely different purpose. Sometimes the answer is hiding in a data set that already exists, waiting for someone to look at it the right way, to ask the right question. Dark matter has been patient for nearly a century. It can wait a little longer. So can we. The long, dark, what remains unknown. We are approaching the end of tonight's journey, not the end of the question. The question has no end in sight, but the end of what we can hold in a single sitting. And so let us settle here. In the open question, in the honest uncertainty, dark matter is real. On this, the evidence is overwhelming. The rotation curves, the gravitational lensing, the CMB, the structure of the universe, the bullet cluster, independent lines of evidence from completely different methods, all pointing to the same conclusion. There is something there, something massive, something invisible, something that makes up 27% of the universe. What dark matter is that remains unknown. Not probably known, not mostly known. Unknown. We have candidates, WIMPs, action, sterile neutrinos, primordial black holes, fuzzy dark matter, things we haven't thought of yet, but we have no confirmed detection, no direct measurement of a dark matter particle, no identified substance. The name dark matter is almost misleading. We are the most scientifically sophisticated civilization in the history of the Earth. We have mapped the genome. We have detected gravitational waves from merging black holes 1 billion light years away. We have landed robots on Mars and a probe on a comet and voyaged to the edge of the solar system. We have built instruments that can detect a single photon from a galaxy formed when the universe was less than 1 billion years old. And we don't know what most of the matter in the universe is. Not sort of know, not have a strong suspicion. Don't know. The universe is under no obligation to be understandable. It is under no obligation to show itself to us. That it has shown us anything that the laws of physics allowed us to deduce the existence of something we cannot see, cannot detect, cannot identify, is already extraordinary. That the universe is comprehensible at all is not obvious. It could have been otherwise. The laws of physics could have been different. The dark matter could have been more dark, interacting so weakly with gravity that its presence was not inferred. Or the universe could have been simpler, no dark matter at all, just ordinary matter and perhaps an occasional modification of gravity. Instead, we live in a universe where something vast and invisible shapes everything, and where the visible fraction can deduce from the motion of stars and the bending of light and the echo of the Big Bang that the invisible is there, and spend a century trying to identify it and not yet succeed, and keep trying. The night sky and the invisible, finding peace in not knowing. I want to come back to that night. The night I pulled over on the side of the road and stood in the dark, looking up, thinking about the invisible. I was not frightened. That is the thing I want to say. I was not frightened by the invisible universe. I was awed. There is a difference. Fear and awe both involve something vast that exceeds us, something larger than we can contain. Fear makes us want to retreat. Awe makes us want to lean in, to look more closely, to understand more deeply, to feel the full weight of what is there. And what I felt that night, looking up at a sky full of light, knowing most of it was pervaded by invisible matter, was the particular awe of a mind encountering something it cannot yet explain, cannot yet understand, cannot yet name, the awe of the genuinely unknown. I think we are afraid of not knowing. As a culture, as individuals, we want answers. We want resolution. We want the narrative to close, the mystery to be solved, the episode to end with the explanation. But the universe is not like that. The universe offers questions that don't resolve, mysteries that persist across generations of human inquiry, and dark matter is one of those mysteries. It has persisted for nearly 100 years. It may persist for 100 more. It may never be fully resolved if dark matter interacts so weakly with ordinary matter that it is fundamentally impossible to detect directly. And I have had to learn, am still learning to be at peace with that, to find not knowing in itself beautiful. Because not knowing is not the same as not understanding. We understand dark matter's role, its effects, its distribution, its history. We know where it is. We know what it does. We know when it became important. We know how it shaped everything. We just don't know what it is. Its identity is particular nature. Its quantum properties, that one thing remains hidden. One answer hidden within a landscape of extraordinary understanding. And the search for that one answer has driven some of the most remarkable science ever done, has built some of the most extraordinary instruments, has produced some of the deepest ideas in theoretical physics. The not knowing has been productive, generative. It has forced us to think harder, to look more carefully, to question assumptions, to invent new methods. The darkness is home. You are in the dark matter halo of the Milky Way. This is simply true. As you breathe, as you rest, dark matter surrounds you, pervades you, passes through you. It has been doing so since before you were born. It will continue long after. The dark matter halo of the Milky Way is ancient. Older than the galaxy's visible disk, it formed first. It provided the gravitational cradle in which the Milky Way assembled itself, in which the Sun found its orbit, in which the Earth condensed from the solar nebula, in which life arose. The dark matter was here before any of this. It is the most ancient structure you inhabit, more ancient than the oldest stars, more ancient than the oldest rocks. A structure that has been here unchanged in its gross distribution for 10 billion years. You are inside something 10 billion years old. The weight of ancient things, what it means to be old. There's a particular quality to things that have been in the world for a very long time. You have felt it in the presence of old mountains, old trees, old stone buildings. There is a stillness to ancient things, a quality of having been present through so much that the ordinary urgencies of the moment seem, in their company, appropriately small. The dark matter halo of the Milky Way has been present through everything, through the formation of the first stars in the galaxy, through the first supernovae, through the slow assembly over billions of years of the disk of stars we call home, through the formation of the Sun, just another star condensing in a spiral arm 5 billion years ago, through the formation of the Earth, through the first life on Earth, through the 5 mass extinctions, through the emergence of complex animals, through the first creatures that looked up, through everything. The halo was there, unchanged, invisible, patient in a way that no living thing can be patient, because patience requires the awareness of waiting, and the dark matter does not wait. It simply is. It simply has been. It will simply continue. When the Sun expands into a red giant and swallows the Earth, when the Milky Way merges with Andromeda, when the merged galaxy slowly loses its stars to the void over trillions of years, the dark matter halo will remain. Diffuse, cold, ancien, the last structure standing when everything else is gone. We are temporary arrangements of ordinary matter, living inside a permanent arrangement of dark matter. The contrast is not frightening, it is clarifying. The other side of the universe, what we can and cannot know, there is a boundary, not a physical wall, not a place you could point to on a map, but a boundary nonetheless, the edge of the observable universe, the sphere of space from which light has had time to reach us since the Big Bang, about 46 billion light years in radius. Beyond that boundary, things exist. We are certain of it. The universe does not stop at the edge of what we can see. The same physics that governs what we observe almost certainly continues beyond our horizon. More galaxies, more dark matter halos, more star-forming nebulae, perhaps structures we have never seen because the particular arrangement of matter beyond our horizon has had an entirely separate 13.8 billion year history from the part we inhabit. Perhaps familiar, perhaps unrecognizable. We do not know. We cannot know, not because our instruments are not good enough, but because the information is simply not there. The light has not arrived. The gravitational waves have not arrived. No signal of any kind can travel faster than light. And so the universe beyond our horizon is, in the most fundamental sense, permanently hidden, not temporarily, not waiting for better technology, permanently, a hard edge to knowledge built into the structure of space-time itself. I find this boundary one of the most profound facts I know, not because it is frightening, but because it is honest. It tells us something true about the nature of knowledge, that there are limits which are not failures, that some things are simply beyond reach, not because we are not clever enough, not because we haven't tried hard enough, but because the universe has a structure that makes certain information inaccessible. And that is not a defeat. It is a description of reality. The universe is larger than what can be known. That is a feature, not a flaw. It means there is always more, always something beyond the horizon, always something the finite mind cannot contain, always something worth wondering about. What happens in the dark, the universe between observations. Most of the universe has never been observed, not just the part beyond our horizon. The vast majority of what is within our observable universe has never had a photon from it reach a telescope on Earth, has never been measured, has never been cataloged, has never entered any human record. It exists. It has always existed. It is governed by the same physics. Stars are forming there right now. Planetary systems are assembling. Chemistry is happening. And none of it is being watched. None of it is being recorded. None of it is entering any mind. The universe proceeds entirely indifferent to whether it is observed. This seems obvious. But there is a tradition in physics rooted in certain interpretations of quantum mechanics that takes observation very seriously. That suggests the act of measurement is not passive, that the observer and the observed are not entirely separate, that in some sense, at the quantum level, things are not definite until they're measured. This is not mysticism. This is physics. Quantum mechanics forces us to ask uncomfortable questions about what it means for something to exist before it is observed. These questions do not have clean answers. They have interpretations, many interpretations, each one strange in its own way. The Copenhagen interpretation, the wave function collapses upon measurement. The definite state is brought into being by the observation. The many worlds interpretation, all possible outcomes occur. The universe branches at every quantum event. There are versions of you in which every quantum decision has gone every possible way. The pilot wave interpretation, particles have definite positions at all times, guided by a wave that exists in addition to the particle itself. Each one is mathematically consistent. Each one is philosophically strange. And none of them changes what the universe does. The mathematics is not in dispute, only what the mathematics means, only what the universe is underneath the equations, and we do not know. We have the most successful physical theory in history, quantum mechanics, tested to extraordinary precision, and we do not know what it is telling us about the nature of reality. The theory works. The interpretation remains open. The universe keeps its deepest secret, the elements returning dust to dust. But older, every atom in your body has a history. We've talked about this before, but I want to go deeper into it tonight. Deeper than the stellar forges, deeper than the supernovae, to the very beginning. The hydrogen in your body, in the water, in your cells, in the amino groups of your proteins, in the methyl groups of your DNA, is primordial, made in the first 3 minutes, when the universe was a hot, dense plasma and protons and neutrons were fusing in the light nuclei. The hydrogen in your body is 13.8 billion years old. It has existed since the beginning of the universe. And in all that time, through all the stellar cycles, through all the geological transformations, through all the biological evolution, it remained hydrogen. The proton at the center of every hydrogen atom in your body has been a proton since the Big Bang. It has been in molecular clouds, in stars, in interstellar space, in the young Earth, in the ocean. in every living thing in your ancestral line, in you, it does not remember any of this. It has no memory, no experience. It is a proton, positive charge, spin one half, governed entirely by the laws of physics, and yet, here it is, in you, part of the most complex arrangement of ordinary matter in the known universe, contributing in its tiny way to the water that makes your cells function, the hydrogen that has always been hydrogen, serving for a few decades a completely new purpose, being part of a mind, being part of awareness, the conversation between forces, how the universe communicates with itself. The universe has four ways of talking to itself, four fundamental forces, four ways that matter influences other matter: gravity, electromagnetism, the strong nuclear force, the weak nuclear force. Everything that happens in the universe, every interaction, every collision, every reaction, every event is mediated by one or more of these four forces. Nothing else. Just four. Gravity holds the large-scale structure together. The planets in their orbits, the stars in their galaxies, the galaxies in their clusters, the clusters in the cosmic web. All gravity, electromagnetic force holds atoms and molecules together. The electrons bound to nuclei by electromagnetic attraction. The chemical bonds between atoms, the light that carries information across space, the electricity in the neurons of your brain that is allowing you to hear these words, all electromagnetism. The strong nuclear force holds the nucleus together, the protons and neutrons bound by the exchange of gluons. Without the strong force, every atomic nucleus would instantly fly apart. There would be no atoms, no chemistry, no matter as we know it. The weak nuclear force governs radioactive decay, the transformation of neutrons into protons, the nuclear reactions in the sun's core that ultimately power all life on Earth, the synthesis of neutrinos in stellar interiors. Full force, operating at different ranges, at different strengths, each one essential. Without any one of them, the universe would be unrecognizable. Without gravity, no structure, no stars, no galaxies. Without electromagnetism, no atoms, no chemistry, no light. Without the strong force, no nuclei, no elements beyond hydrogen. Without the weak force, no nuclear burning in stars, no supernovae, no distribution of heavy elements. The particular values of these four forces, their strengths, their ranges, their mathematical properties, seem to be fine-tuned for complexity, for structure, for chemistry, for life. Whether this is genuinely remarkable or simply the inevitable observation of any mind that finds itself in a universe complex enough to contain it is a question physics cannot fully answer. It is a question that sits at the boundary between science and philosophy, between what can be measured and what can only be wondered at. Neutron stars, the universe at its densest. Let me take you to the densest places in the universe that are not behind an event horizon. Neutron stars, the collapsed cores of massive stars, after the outer layers have been expelled in a supernova. What remains at the center, a sphere of nuclear matter, approximately 20 kilometers in diameter, containing between 1 and 2 solar masses, 1 to 2 times the mass of the sun, compressed into a sphere the size of a city. The density of a neutron star is extraordinary. At its core, the density may exceed that of an atomic nucleus. Matter packed so tightly that individual protons and neutrons lose their identity, dissolving into a soup of quarks and gluons, a state of matter that does not exist anywhere else in the current universe, a state we have never been able to create in a laboratory, a state we can only infer from the equations and from the behavior of neutron stars at a distance. At this density, a teaspoon of neutron star material would weigh approximately 1 billion tons. Not 1 billion tons for the whole teaspoon, 1 billion tons per teaspoon. If you removed a teaspoon of neutron star material from the star and placed it on the surface of the Earth, it would immediately fall through the Earth, straight through. The gravitational attraction between that tiny object and the Earth would be overwhelming. It would pass through the crust, through the mantle, through the core, out the other side, oscillating back and forth through the center of the Earth, like a pendulum made of the densest ordinary matter the universe creates. Ateaspon, falling forever. Pulsars, the heartbeat of dead stars. Some neutron stars spin rapidly. When the core of a massive star collapses, conservation of angular momentum dramatically increases the rotation rate. Like a figure skater pulling their arms in. The result, neutron stars that rotate dozens, hundreds, sometimes thousands of times per second. And many neutron stars have strong magnetic fields, extraordinarily strong, perhaps 1 trillion times stronger than the Earth's magnetic field. Where the magnetic field of a spinning neutron star is not aligned with its rotation axis, the field sweeps through space like a lighthouse beam, and along that beam, radiation is emitted, radio waves, X-rays, gamma rays, a periodic pulse, once per rotation, arriving at Earth with extraordinary regularity, more regular than the most precise atomic clock on Earth. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, a graduate student at the time. She was monitoring radio signals from a radio telescope in Cambridge, and she noticed something strange, a signal that pulsed with perfect regularity, every 1.33 seconds. So regular, so precise, that she and her supervisor briefly wondered if it was artificial, a signal from something other than a natural astrophysical source. They designated it LGM1, Little Green Men, half joking, because nothing natural was known to produce such perfect regularity. It was, of course, natural. It was a pulsar, a rotating neutron star, the most precise natural clock in the universe. Jocelyn Bell Burnell made one of the great discoveries of 20th century astronomy. Her supervisor, Anthony Hewish, received the Nobel Prize. She did not. Some stories take a long time to be properly told, but her discovery stands as unambiguous as the signal itself, pulsing, regular, the heartbeat of a dead star, continuing long after the star is gone. The magnetar, when physics reaches its limits, some neutron stars have magnetic fields so extreme they deserve a separate name. Magnetars, neutron stars with magnetic fields 1,000 times stronger than ordinary neutron stars, perhaps 1,000,000,000 times stronger than the Earth's magnetic field. At the surface of a magnetar, the magnetic field is so intense that it would affect the quantum mechanical properties of the vacuum itself. It would change the way light travels through empty space near the star. Light would be bent, split, polarized in ways that do not happen in weaker fields. The vacuum, which we think of as empty, would behave as a medium. A magnetar would distort the space around it in ways that go beyond ordinary electromagnetism into the realm of quantum electrodynamics, the relativistic quantum theory of light and matter, theory that has been tested to extraordinary precision in laboratories, but never in a field this strong. A magnetar is the only place in the universe where we could test quantum electrodynamics in a regime we have never accessed. If we could get close enough, if we could survive, which we could not, at a distance of 1,000 kilometers from a magnetar, the magnetic field would be strong enough to strip the electrons from the atoms in your body, to distort the electron clouds of every atom in you. Beyond that distance, closer, the effects become more extreme. Magnetars occasionally release bursts of energy, starquakes, fractures in the rigid neutron star crust, releasing in a fraction of a second more energy than the sun releases in 100,000 years. The most energetic events in the known universe, short of black hole mergers and supernovae. In 2004, a magnetar burst reached Earth from 50,000 light years away. Briefly saturated our gamma ray detectors, ionized the upper atmosphere. From 50,000 light years, the universe can reach us from a very long distance in ways we do not always expect. The speed of things, motion in the universe that never stops. Nothing in the universe is still. Nothing. You are sitting or lying, apparently still, but you are moving. The Earth rotates. You're moving at about 400 meters per second due to the rotation of the Earth. Depending on your latitude, the Earth orbits the Sun. You are moving at about 30 kilometers per second relative to the Sun. The Sun orbits the center of the Milky Way. You are moving at about 220 kilometers per second relative to the galactic center. The Milky Way moves relative to the local group. The local group moves relative to the Virgo supercluster. The Virgo supercluster moves relative to the cosmic microwave background. At each scale, a new motion, a new velocity, adding together into a total velocity that is difficult even to define. Relative to what? Every velocity is relative. There is no absolute rest, no cosmic reference frame. The universe has no center, no edge, no preferred direction. Motion is always relative to something else, and everything is moving relative to everything else. The atoms in your body are vibrating. Thermal motion, the faster the temperature, the faster the vibration. The electrons in your atoms are in constant motion, not orbiting the nucleus like planets orbit the sun. That model is too simple. They exist as probability distributions, quantum clouds, never at rest, never in one place, defined not by position but by the probability of being found at a position. Moving, always, even at absolute zero, which cannot be reached, there would be 0-point energy. Quantum fluctuations, motion that cannot be removed. Motion built into the structure of reality by the uncertainty principle. The universe is never still, not at the largest scale, not at the smallest. Motion all the way down, motion all the way up, and you, apparently at rest, participating in all of it, moving with the Earth, with the solar system, with the galaxy, vibrating with your own thermal energy, sustained by the motion of electrons in your neurons. The stillness you feel is not the absence of motion. It is the sensation of motion so consistent and so embedded that it disappears from perception, becomes background, becomes normal, becomes the felt sense of rest that is, in reality, a vast and layered participation in the motion of everything. The chemical universe, how carbon changed everything. There is one element that deserves special attention. Not because it is the most abundant, not because it is the most exotic, but because of what it does. Carbon, the element with 6 protons, the fourth most abundant element in the universe by mass. Carbon has a property that no other element has to the same degree. It can bond with itself repeatedly, forming chains, rings, branching structures, networks of extraordinary complexity. A silicon atom can form 4 bonds. Carbon can form 4 bonds too. But carbon-carbon bonds are stable in a way that silicon-silicon bonds are not. At the temperatures and in the chemical environments found on planetary surfaces, carbon can form chains of thousands of atoms, rings of 6 that stack into sheets, sheets that roll into tubes, structures that fold and twist and wrap around each other with precision. No other element does this with the same stability, with the same variety, with the same capacity for complexity. Carbon chemistry, organic chemistry, is the chemistry of complexity, of information storage, of catalysis, of self-replication, of the molecular machinery of life. DNA is a carbon structure. Proteins are carbon structures. Cell membranes are carbon structure. Every mechanism of life, every enzyme, every receptor, every signaling molecule is built on a carbon framework. Carbon is the element that made life possible on Earth, and perhaps everywhere. Perhaps life elsewhere, if it exists, is also carbon-based, because carbon is the element best suited to the job, not because the universe designed it that way, but because the physics of chemical bonding, which emerges from the quantum mechanics of electrons, gives carbon its unique properties. The universe produced through the triple alpha process in stellar cores, an element perfectly suited to store information and catalyze reactions. Not by design, by physics. And in at least one place, this small rocky planet, that chemistry took on a life of its own. Literally, the ocean as origin, where life began 4 billion years ago. The Earth is young, still being bombarded by asteroids and comets, the last remnants of the solar system's formation. The impacts bring water, bring carbon compounds, bring the raw materials for chemistry. The surface is hot. The atmosphere is nothing like what it is today. No oxygen, mostly nitrogen, carbon dioxide, methane, hydrogen sulfide. A reducing atmosphere, chemically active, and somewhere in the shallow coastal waters, or in the deep ocean at hydrothermal vents, the chemistry begins to organize itself. Simple molecules, amino acids forming from simpler precursors, lipids self-assembling into membranes, RNA-like molecules beginning to catalyze reactions, beginning to copy themselves, imperfectly at first, but copying the key step, the first step toward life. Not an organism, not a shell, just a molecule that could make copies of itself, that could pass information to the next generation, that could, through variation and selection, improve at the copying over millions of years. From this beginning, through stages we do not fully understand, through transitions we cannot fully reconstruct, from chemistry to biochemistry, from biochemistry to the first true cell, a cell with a membrane, with a genome, with the molecular machinery to read that genome, to copy it, to use its information to build proteins, the first cell, the ancestor of everything, the ancestor of every organism that has ever lived on this planet, including you. You share a common ancestor with every tree, every insect, every bacterium, every fungus, every fish, every bird. One ancestor, 4 billion years ago, in the ocean, a molecule that figured out how to copy itself. That is where you come from. Ultimately, below all the history, below all the evolution, below all the complexity, a molecule in water, copying itself, the tree of life. 4 billion years of becoming. 4 billion years is a long time. Long enough to go from a self-replicating molecule to a mind wondering about self-replicating molecules. In that time, in the approximately 4 billion years of life on Earth, evolution has produced something in the range of 5 billion distinct species. 5 billion, most of them gone. The vast majority of all species that have ever lived are extinct. Gone before any human eye could see them. Gone before any human mind could name them. Existing for their time, shaping the environment for those that followed, and then gone. This is the pattern. Life is not a ladder with us at the top. It is a bush branching in every direction. Every living thing is equally evolved, equally adapted to its niche. The bacterium that has been a bacterium for 4 billion years is not a failure. It is a success, extraordinary success, the most abundant form of life on Earth, occupying every habitat, every extreme, hot springs, deep ocean vents, polar ice, the inside of rocks. The human gut, bacteria have conquered every environment this planet offers. And they did it 4 billion years ago. Before any complex organism existed, we are the newcomers. Complex multicellular life has been around for perhaps 600 million years. Animals with brains, perhaps 500 million. Mammals, perhaps 200 million. Primates, perhaps 60 million. Genus Homo, perhaps 2 million. Modern humans, perhaps 300,000. In the 4 billion years of life on Earth, we have been here for less than 0.01% of that time. The bacteria were here first. They will be here last. We are a brief experiment, a new branch, remarkable in some ways, not permanent, not inevitable, just the current result of a process that has been running for 4 billion years, with no destination, no endpoint, no purpose other than the ongoing reproduction of information, the ongoing becoming of things, what intelligence is, the universe thinking about itself. Intelligence is not one thing, it is many things, and we are only beginning to understand what it is in ourselves. The human brain contains approximately 86 billion neurons, each neuron connected to thousands of others. The total number of synaptic connections, the junctions between neurons, is estimated at around 100 trillion, a number comparable to the number of stars in 1,000 Milky Ways. The brain is, in terms of connection density, the most complex object we know of in the universe. Not in terms of size, not in terms of energy, but in terms of the density of connections, the richness of the network. And from this network, from the electrical and chemical signaling between neurons, something emerges: thought, perception, memory, language, mathematics, art, the capacity to look at the night sky and ask, what is there? We do not understand how this emergence happens. We can describe the neural correlates of thought. We can watch patterns of activity in the brain as thoughts occur, but we cannot explain why those patterns feel like anything, why the activity in a network of neurons produces the subjective sensation of understanding, of curiosity, of wonder, This is the hard problem of consciousness. It may be the hardest problem there is, not because it is mathematically difficult, but because it is conceptually strange. It requires explaining not just what happens, but what it is like for something to happen. And physics, as powerful as it is, describes what happens. It does not yet describe what it is like. The gap between those two descriptions is where the deepest mystery lives. And you are that mystery right now, lying still, thinking these thoughts, feeling something. You are the part of the universe that has not yet explained itself to itself. Time and memory, the past that still exists. The past is not gone. This sounds wrong. The past is over. The past is, by definition, no longer happening. How can it not be gone? But consider, light from the sun takes 8 minutes to reach us. When you look at the sun, you are seeing it as it was 8 minutes ago. The 8-minute past sun. When you look at the nearest star, Proxima Centauri, you are seeing it as it was 4 years ago. When you look at the Andromeda galaxy, a faint smear in the northern sky visible to the naked eye, you are seeing it as it was 2.5 million years ago. The light that enters your eye from Andromeda left that galaxy when our ancestors were Homo habilis. When stone tools were a new invention, the past still exists in the light. The past is encoded in every photon traveling through space. It has not been erased. It is still arriving, and not just in light, in everything. Every signal that travels at the speed of light carries information about the state of its source at the moment it was emitted. The universe is full of messages from the past, arriving continuously. The cosmic microwave background is a message from 380,000 years after the Big Bang. It is arriving now. It was arriving yesterday. It will be arriving tomorrow. The past is present, encoded in radiation, filling the universe. And memory, human memory, is a kind of light, a signal that carries information about past states. Not perfectly, not without distortion, but carrying something of what was into the present. You carry within you not just your own memories. You carry the evolutionary memories encoded in your DNA. The 4 billion years of biological innovation that shaped your genome, the immune responses evolved over millions of years. The neural architecture inherited from ancestors who needed to navigate complex social environments. The deep structures of language and perception, the capacity for love and fear and curiosity, all of it is memory. All of it is the past persisting into the present. You are not just a person, you are a vessel of time carrying the past forward into a future that does not yet exist. What silence contains, the space between signals, the kinds of silence, the silence of a room at night, the silence between musical notes, the silence between words in a conversation, the silence of deep space. Each one different, each one containing something. The silence of the room contains the small sounds, the settling of the house, the distant hum of a city, the sound of breathing that are only heard when the larger sounds stop. The silence between musical notes contains the resonance, the memory of the note just played, the anticipation of the note to come. The silence between words contains meaning, pause, emphasis, the space that makes the words distinct. The silence of deep space, the interstellar medium, is not empty. We have talked about this. It contains gas and dust and magnetic fields and cosmic rays. It contains the slow, cold chemistry of molecular clouds, where complex molecules form on the surfaces of dust grains, in temperatures close to absolute zero, in darkness, in silence. Amino acids have been found in interstellar clouds, the precursors to proteins, the building blocks of life, forming in the darkness between the stars. Not on the planet, not near any warmth. In the cold space between, the silence is not empty. The silence is where the preparation happens. The chemistry of the future, building itself quietly, in the dark, between the lights. The anthropic question, why this universe? There is a question that sits at the edge of science, that some physicists regard as scientific, that others regard as philosophical, that perhaps cannot be fully separated from either. Why does the universe have the properties it has? Why is the gravitational constant what it is? Why is the charge of the electron what it is? Why is the mass of the Higgs boson what it is? If any of these constants were slightly different, very slightly, the universe would be radically different. If gravity was slightly stronger, the universe would have collapsed back on itself before any stars could form. If gravity was slightly weaker, the matter would have dispersed too quickly. Stars would never have condensed. If the strong nuclear force were slightly weaker, protons and neutrons would not bind. Nuclear would not exist, no elements beyond hydrogen. If it were slightly stronger, all the hydrogen in the early universe would have fused into helium. No hydrogen stars, no hydrogen for water, no hydrogen for organic chemistry. The constants of physics appear to be fine-tuned for the existence of complexity, for the existence of chemistry, for the existence of life. Why? There are several answers, none of them fully satisfying. The multiverse answer, there are many universes, each with different constants. We find ourselves in one with the right constants, because only in such universes can minds exist to ask the question, the selection effect. Of course, we find ourselves in a universe compatible with our existence. There is no other kind of universe we could find ourselves in. The design answer, the constants are what they are because of intention. The answer that physics currently has no tools to evaluate. The inevitability answer, perhaps the constants could not have been different. Perhaps there is a deeper theory not yet found from which the constants emerge as necessary consequences. A theory in which the constants are not free parameters but derived results. These answers are not exclusive. Multiple might be true simultaneously, and the question may not have a final answer. It may be one of the permanently open questions, the ones that push at the boundary between what can be known and what can only be wondered. The returning light, what telescopes have given us. In 1609, Galileo Galilei turned a telescope toward the sky. He saw what no human had seen before. Moons orbiting Jupiter, the phases of Venus, the mountains of the moon, stars invisible to the naked eye. The Milky Way resolved into individual stars, a universe much larger than the one he had been born into. In that moment, in the act of extending human sight beyond its natural limits, something changed, not just in astronomy, in the human relationship with the universe. The telescope said, you can see further, you can know more. The universe is not the size of your unaided perception. It is larger, always larger. And every generation since has built larger telescopes, sent telescopes into space, open new wavelength ranges, radio, infrared, ultraviolet, X-ray, gamma ray. gravitational wave. Each new window revealing a universe invisible to the previous generation. Each new telescope a vote of confidence in the project of understanding. The James Webb Space Telescope, a mirror 6.5 meters across, cooled to within a few degrees of absolute zero, orbiting 1.5 million kilometers from Earth, is the current furthest reach of that project. When it images galaxies whose light has been traveling for 13 billion years, it is continuing something Galileo started. The extension of human sight, the refusal to accept the limits of the naked eye, the insistence that the universe can be seen, can be known, can be understood, not completely, not finally, but more each generation, more each decade, more each new instrument. The project continues. What we're doing here, the purpose of understanding, why do we do this? Why spend lives studying things so distant they can never be touched, so ancient they can never be revisited, so vast they can never be encompassed? The answer is not simple. It is many things at once. Curiosity, the oldest and most fundamental driver of human inquiry. The need to know what is there, what it is, how it works. Curiosity that does not need a practical justification. That is its own justification. That is perhaps the purest expression of intelligence. The desire to understand for its own sake, wonder, the emotional dimension of curiosity, the response to the sublime, the feeling of standing at the edge of the knowable and looking out, the experience of understanding something profound. The moment when the equations click into place, when the data reveals a pattern, when the invisible becomes visible through the right instrument, these experiences are among the deepest that human minds report, among the most meaningful, among the most worth having. Context, the practical value of perspective, knowing that you are a temporary arrangement of atoms on a small rocky world, that the universe existed for 9 billion years before you, that it will exist for trillions of years after, that the concerns of the day, real and important as they exist within a larger frame, a much larger frame, the frame of stars and galaxies and dark matter and deep time. This perspective does not diminish the concerns. It does not make anything meaningless, but it scales them correctly. It places them within their true context. And from that context, something clarifies. What matters? What is temporary? What is permanent? What is worth the limited time we have? The limits of the self? What the universe teaches about boundaries? We think of ourselves as separate, a bounded self, a skin-enclosed individual, distinct from the air outside, from the ground beneath, from other people, from the universe. This sense of self is real. It is functionally important. It is what allows you to navigate a world of distinct objects and causal relationships. But it is also, in some sense, an approximation. The atoms that compose you are not permanently yours. You exchange atoms continuously with the environment, through breathing, through eating, through the constant turnover of cells. Every atom in your body was elsewhere 5 years ago. Most of it will be elsewhere in 5 years. You are more like a river than a stone, a pattern that persists, a form maintained through constant material flux. The atoms are temporary residents. The pattern is what persists. And the pattern, the information that makes you, you emerged from the pattern that came before, from your parents, from their parents, from an unbroken chain of patterns stretching back to the first cell, to the first self-replicating molecule, to the chemistry of the early Earth. to the carbon forged in stellar cores, to the hydrogen from the Big Bang. The self, the pattern that you are, is continuous with everything, not metaphorically, materially, informationally. The boundary between you and the universe is real enough for practical purposes, but thin, permeable, temporary, and underneath the boundary below the level at which the self can be distinguished from what it came from, there is no separation. There is only the universe, arranged into many forms, one of which briefly is you, the softening, coming back. We have been far tonight, further than before, perhaps, into the invisible matter that holds the galaxy together, into the neutron stars and magnetars that push physics to its limits, into the question of why the universe is what it is, into the nature of consciousness looking at itself, into the continuity between the self and everything. And now, as every journey eventually does, this one comes back, not because it is over, not because the questions have been answered, but because the body needs rest, and the mind, having stretched as far as it can stretch tonight, is ready to release the holding, to let the vastness recede, not disappear, just soften into background, into the texture of the night, the way the sound of rain softens into something you no longer hear. But that is still there, still happening, still real. The dark matter is still there, surrounding you, passing through you. The neutron stars are still spinning, sending their pulses into space. The Tarantula Nebula is still forming its stars. The cosmic web still holds its ancient structure. The James Webb Space Telescope is still looking, still receiving, still translating the ancient light into images, into understanding. All of it still happening, as it always happens, with or without your attention, with or without any attention at all. The universe does not require witnesses, but it has produced them in you, in the particular arrangement of carbon and water and electricity that is lying still right now. Breathing, letting the concepts dissolve. Onebuan, the way stars dissolve into the sky as the eye adjusts, becoming background, becoming simply night, the breath that remains right now, nothing else, the breath still here, steady, patient as the red dwarf stars, burning slow, in and out, the oxygen entering made in massive stars that transformed billions of years before the Earth existed. The carbon dioxide leaving the same carbon that has cycled through the biosphere for 4 billion years. The nitrogen that makes up most of the air, the most abundant gas in the atmosphere, assembled there by billions of years of biological nitrogen cycling. Every component of this breath has a history that stretches to the beginning of the solar system, or beyond. And it is happening right now, without effort, without intention. The body knowing what to do, as bodies have always known, since the first organisms developed the need to exchange gases with their environment. 4 billion years of breathing. In the lineage that led to you, this breath is part of that lineage. This quiet, ordinary, unconscious breath is 4 billion years old in its origin, and happening right now, in this room, in this body, in you. There is nothing you need to do. The breath will continue. The heart will continue. The dark matter will continue to pass through you. The earth will continue to turn. The galaxy will continue its slow rotation, 220 kilometers per second, around the center that is, right now, exactly where it has always been. 26,000 light years away. Patient, ancien, indifferent, and around that center, on one of four spiral arms, in an unremarkable region of a medium-sized galaxy orbiting a middle-aged star, this planet, this room, this body, this breath, this moment, which is, in the context of everything, immeasurably small, and in the context of the only thing that can experience anything, everything, absolutely everything, the last thought before sleep takes it, there will be a last thought tonight. You do not know which one it will be. It will come without announcement. The way sleep always comes, not when you try to reach it, but when you stop trying, when the effort of maintaining consciousness becomes too much and the mind lets go, drops into the quiet, the darkness that is not like the darkness of space, the darkness that is warm, safe, internal, the darkness of rest. On the other side of that darkness in the morning, the light will return. The sun, 8 light minutes away, will have moved through its arc. The earth will have turned enough. The room will fill with a different quality of light, and you will wake reassembled. The pattern that is you reconstituting itself from the state of sleep, and the universe will still be there. The dark matter still holding the galaxy together. The pulsars still spinning, the cosmic web still stretching across hundreds of millions of light years. The James Webb Space Telescope still gathering photons. The questions still open, still unanswered, still beautiful in their openness. And you, the part of the universe that asks questions, will be there too, ready to ask them again, but not yet, not tonight. Tonight the questions soften, the numbers dissolve, the distances fold themselves away. Everything that is vast becomes, in this moment, small enough to rest inside, small enough to breathe around, small enough to sleep in the presence of. The universe is not asking anything of you. It never has. It is simply there, as it has always been, and you are in it, as you have always been. The dark matter surrounds you. The ancient light passes through the night. Somewhere, a pulsar sends its regular pulse into the void, and in a room, on a planet, in a galaxy, in a universe that is mostly invisible, something small and warm and aware lets go and sleeps